So hello everyone, welcome to the fifth lecture of this week. So we are talking about word embeddings. So in the last lecture we discussed what is the different ideas behind using word embeddings, what can be some interpretation given to the different dimensions here, and what are different tasks where you can use these word embeddings. But we did not go through the learning part. How do we actually obtain these word embeddings for different words? So today in this lecture we will try to discuss in detail how do we obtain these embeddings. So in the last lecture we discussed that there are two different models for word embeddings. So there are two main models. One is continuous bag of words model and another is skip graph model. What is the idea there? In continuous bag of words model, using the neighboring words, I am trying to predict the center word. In a skip graph model, using the center word, I am trying to predict the neighboring words. So let us see what we do in CBOW model. So here, let us say we have a approach like this. The recently introduced continuous skip graph model is an efficient method for learning high quality distributed vector representation and so on. So, this is the text data that I have, suppose, and I'm trying to learn representations of various words, embeddings. So, at a time, I'll go through one particular window here. So, I'll focus on a word. So, let us say I am focusing on one word like learning. Okay. So, what I will do, I'll take a window around that word. Now, window size can vary, and this can be a hyperparameter that you will choose. So, you can choose, say I will take 4 words before that and 4 words after that. So, using these 8 words around this word learning, I'll try to predict this word learning. So, how do we do that? So, yes. So, imagine a sliding window over the text that includes the central word and with 4 words that precede and 4 words that follow it. So, like here, learning is my focus word and there are 4 words before it and 4 words after that. And you can also call them as the context words. And using the context words, you are trying to predict the focus word. So this is some sort of network representation and how this learning will take place. So you are seeing here in the input you have various column vectors. So what do I mean by this? So here, so what you are doing, you are putting in one hot encoding as the input. So I have this column vector of size v. So this is the column of size v. Now, so v is the size of my vocabulary. I have that many words in my vocabulary. So I may not use this, only v. Okay, v is the size of my vocabulary. Now, in your context, you are having certain word that will be there in the vocabulary. So let us see, this is the index of that word. So this input would be everything else as 0 and this will be 1. Okay, this is a one hot encoding of that word. It's a column vector. So like that, in your context, suppose you have here 8 words. So you'll feed all these 8 one hot forms. So here it might be 1 here, 0 here, it might be 1 somewhere and everything else 0. Okay, that is your input that you are feeding. Now, using this input, then you are having a hidden layer. This is n dimension. Okay, and remember this n will be important. We will see what is this n. So now this is size v. Now I want to map these to this n dimensions. So I'll have a weight matrix let us say W1 of dimension. So this is v cross 1. Sorry, so this you can take it as 1 cross v. So you will have it as v cross n. Okay, so that the final representation is n dimensional. Now, so you will have the same weight matrix at each input. So you'll get, and then you can take the average of all these. Now from this n dimension, you again go to your v dimension. This is your output layer. So what will be the second weight here? This will be n cross v. Okay. So you are starting with a v dimension, going to n dimension and hidden, and then going to the v dimension in the output. Now, so what you are doing here, so before going into what are the connections in the network, you are putting some inputs that are your context words. So suppose you are having 8 different one hot vectors, and whatever happens here, finally you are trying to predict your center word. This should be your center word. Okay. So what will happen here? You will have various weights, W1, Wn, some numbers you will get, Wv, some v different numbers you will get, and you want to ensure that the actual center word, suppose this is my center word, this has the highest probability, and if it is not having the highest probability, you will try to modify the weights in your network so that it gets a higher probability than what it is getting right now. So now let us see what do we mean by all these connections. Okay. So what would happen from here? So let us go back to the slides. So each word is encoded in one hot form, that is here. You have a single hidden layer and an output layer. So you are having two different weight matrices. One is v cross n, another is n cross v. Okay. So from input you go to hidden, from hidden you go to output. Output you are trying to predict the center word. So what is my training objective here? So you see, I am getting some word, some numbers for different all my v words at the output layer, and this you can think of as the probability value. And you might have a question that how do I convert these numbers to probability? We will see that. So assume that you are having v different probability values. Now you want to maximize the condition probability of observing the actual output word given the input context word with regard to weights. So you will say that I want to maximize the probability that I will obtain the actual word that I saw in my input and not any other word. So whatever probability I am getting, that becomes my objective function. So I want to maximize this condition probability of output word given all my input words, and this probability will be expressed in terms of all these weights that I am having in my network. So in our example, what would happen? I am giving this input, all these 8 words, an efficient method for high quality distributed vector, and I want to maximize the probability of getting learning as the output. This is my center word. Now, so what happens from input to the hidden layer? So input, we are saying we are feeding one hot vectors. So if there are 8 different input words, I am having 8 different one hot vectors. Now what do I mean by multiplying this one hot vector with my first weight matrix, that is of dimension v cross n? So you can think of it like that. So you put using an input, so this is one word, and having a corresponding element as 1, that is my input word, and you are multiplying it with v cross n weight matrix. So this operation is nothing but you are taking the corresponding row of this matrix. This matrix has v different rows, so these v rows you can think of as if corresponding to v different words in my vocabulary. So whenever you are feeding a one hot form of one word, you are picking up that row. Okay, and so you are doing it for 8 different words. So you are picking 8 different rows in my initial weight one matrix, and then so you are having given c input words. So active function for the hidden layer will be simply summing the corresponding hot rows. So I'll pick up the hot rows here that correspond to the input words and divide by c, so that I have an average representation. So now you understand what is going from input to hidden layer. You are taking c different rows from your weight matrix and averaging those. That's what goes in your hidden layer. Now what happens from hidden to output layer? So remember, we have a second weight matrix W2 that goes from hidden to output layer, and its dimension is n cross v. So now hidden layer dimension is 1 cross n. So if I multiply this 1 cross n matrix with this n cross v matrix, I will get a 1 cross V matrix. Okay, and that is my output layer. So these 1 cross V matrix you can think of as having weights for different words in my vocabulary, and I want to maximize weight for my center word. Okay. So from the hidden layer to output layer, the second weight matrix W2 can be used to compute a score for each word in my vocabulary, and now so you can obtain the weights. How do you convert them to probability values? And for that you use softmax. What is the idea of softmax? So here you will get the weights W1 to WV. They can be any real numbers. Okay. Now how do you convert that to probability distribution? So this is a simple idea that is in softmax. So in softmax, what you do is you are given W1 to WV, and you want to convert that to a probability distribution. So you will say that I'll simply multiply all these by, so I will put an exponent over these. So e to the power W1, e to the power WV. Now they are all positive numbers, and then to convert them to probability, I'll just divide it by summation over E Wi for all I. Okay. So now this will sum up to 1 because this is normalized, and these are my probability distribution. So I have these weights. I use a softmax to convert them to probability values, and then I will try to maximize the probability of my actual center word. This will become my training objective, and based on that I will learn my weights. Okay. So I'll talk a bit about this learning problem when I go to the next model of skipgram. But suppose we have some way of learning these weights, and finally I have the optimal set of weights W1 and W2. Now where are the word vectors? What are your word vectors? Here I am feeding one hot vector. This is not being learned. This is the same. So where are my word vectors being learned? Now if you think about it, so what I am learning are the weight matrices. Okay, this is of V cross N, this is N cross V. So I can take a transpose, this also will become V cross N. So you can think of it as if for each word you are learning a n dimension representation. Okay. So after you learn this matrix, these weight 1 and weight 2 will correspond to your word embeddings. Okay. So W1 will be of size. So W1 will be of size V cross N. So you can take any vector I and get a n dimensional representation, and this n you can also think of as your d dimensional representation. Okay. So for each word you are getting a d dimensional vector. Similarly for W2 you will get, similarly if you take a transpose you will get a V cross N representation. So, and in general what you do, you can take a so you are getting two vectors, one from W1, one from W2. So you can finally combine these two vectors. You can either concatenate these vectors for the same word, or sum these over, or take an average, and that works fine. So this is the intuition about what is the kind of network that you use for learning these embeddings. Okay, so these weights are nothing but my embeddings that I am learning. Okay. So this is about continuous backwards model. Now what will happen in skipgram? In a skipgram model, the network will slightly change. So now I will feed only the center word here, only one input vector, but I will predict multiple context words. Okay. So now from input to hidden there are only one, only one input vector, but output there are multiple vectors. So let us look at the skipgram model. So skipgram model is just the opposite of CBOW model. So you have the center word as a single input vector, and the target context words are at the output layer. So this is my output layer, and you can now very easily correlate with what we did in CBOW. So the weights correspond to roughly the same idea. So now let us formally define. So we see how using the network we can think about the learning, how the learning will take place, and how the weight updates will take place. But suppose you want to write it mathematically, then how do we do that? So, so yeah, this is very analogous to what we saw in the case of CBOW. So here, from input to hidden layer, I am simply copying the row from the weight matrix W1. So I am having only one input, so I will copy only one row, and that will go to my hidden layer. Now at the output layer, we will have C different distributions, and I will try to predict the C different context words using my hidden layer. And objective is to maximize the summed prediction error across all the context words in my output layer. So I want to predict all the, so I want to maximize the probability for observing my actual context words. So let us say we have a window where I am having small c words in the left, small c words in the right. So what can be my training objective? It can be, I am trying to maximize, suppose I take log probability W t plus j given W t. So W t is the center word, and I am going from minus c less than equal to j less than equal to c, window of size c around j, and j is not equal to 0. And this I can do for all possible center words, and this becomes my training objective. Okay, so we will see that. So I am predicting surrounding words in a window of length c of each word. My objective function is, I want to maximize the log probability of any context word given the current center word. So I am trying to maximize this probability of W t plus j given W t, and sum over all the possible context words, and then I can sum it over all the possible words in my input, and this becomes my overall objective. So j theta, and theta have all the parameters, all the weight matrices W1 and W2 that I am trying to learn. So now this is my objective function, and I want to maximize that, and by doing that I want to learn my parameters theta. And how do we do that? So firstly, let us see how will we compute these probabilities. Probability W t plus j given W t. Now this will be actually, you have already seen that in the case of using the network, but using these some mathematics can we show that. So idea is that, let us say I am having a probability for P W O given W I. So W I is my context word, and W is the output word. That is the, I am sorry, so I should say as the center word, and this is my output word. These are all the context words. Okay. So let us say for a given context words, how do we write it? And I am saying we can write it in this form, that is exponent V prime W O transpose V W I divided by sum over W is equal to 1 to capital W V prime W transpose V W I. Okay. And this is a formulation of this probability, and let us try to understand that. So what are the different things we have written here? So one thing you are seeing, there is a V and there is a V prime. So for each word you have two vectors, one is V, another is V prime. So V is for the, so V is used only for the input, center word, and V prime is used for output. So when I am trying to use the input word to predict the output word, I will simply take a dot product of these. Now both these vectors are like column vectors. So VWI will be of this form, and V prime WO will also be as a column vector. So how do I get a number? By multiplying these two, I will take a transpose of this, okay, and multiply with this, and that's what I am doing here. V prime W transpose times VWI. That gives me a single number. Now this number I want to convert to a probability value. So then I am using a softmax over that. Exponent over this number divide by, I will do it for all the words in output. Okay, so that's why I have a summation over all the words. W is the total number of words in my vocabulary. So this is nothing but a probability distribution, and you can see that summation P WO given WI for all words WO will add up to 1 because of this normalization factor. This will add up to 1. So this is giving me a conditional probability of WO given WI. Now as a simple exercise, you can also try to see how this number comes from the network that we talked about. Okay, so we had a network interpretation. Now we have a simple matrix sort of interpretation. So how they correspond to each other, and they use the idea that weights 1 and weights 2. What are these? Weight 1 correspond to the input and weight 2 correspond to output. Use this idea and see that by using the network also, are you getting the same form of this probability by putting softmax over the output layer, and you will see that you are actually getting the same form. So now I have this formulation W given WI, this particular formulation, and I put it here for all the words in my context, and this becomes my J theta. This is my objective function. Now what is my objective? I want to learn my V and V prime. So I will try to learn my V and V prime such that this is optimized, and for that there is a simple way, that is you can use gradient descent algorithm. So you can try to take partial derivative of J theta with respect to each of these parameters and update your weights accordingly. So this is the probability conditional probability distribution function that we have found, and V and V prime are input and output vector combination of the same word W. So every word has now 2 vectors. So suppose I have d-dimensional vectors. So D is my so D is the dimension of my hidden layer in the network terms, or for each word what is the representation that you are using? You are using a d-dimensional representation. So I have V many words. So what is the size of my parameter theta? So I have capital V words. For each word I have an input vector and output vector. So there are 2 V vectors and each vector is of dimension D. So I have 2D times capital V, that many parameters to learn. This is my whole set theta. And what is the simple gradient descent formula? So this is like you take the derivative with respect to the that particular parameter. So theta j new is theta j old minus alpha is my learning rate, and you take a partial derivative of j theta with respect to the parameter while putting the old values. Now I am supposing that you know the idea of gradient descent that is used to optimize or minimize a particular function. So if I want to give this idea very briefly, so this is like, suppose you have a simple function like this, and I want to find out for what parameter theta or for parameter x. So suppose this is a function over x and this is my y. For what value of x this is minimized. So what I will do, I will start with any x. Okay, so suppose I am starting with this x0. I will find out the value of function. So I go to the function. So y is suppose fx0. Now I want to know what is the value of x where this is minimized. So what I will do, I will take the derivative of the function at this point, f prime at x0, and so now I have to minimize. If this is the direction of my gradient, I have to go in the opposite direction of my gradient. So my new value should be x naught minus f prime x naught. So I will go in the opposite direction and I will use some learning rate, with what rate you will go in this direction. And this is simply the idea of gradient descent. You keep on doing that. So you go somewhere, again you find the, suppose you are going at this point, okay. So now your gradient will point you to this direction, so you will try to go in this direction. Again gradient will point you some direction, and finally you will converge. So this is a very simple idea of gradient descent, but I will suggest that you have a look at it, that what is actually gradient descent. So this is a simple function, but your function can be over multiple parameters. So like here I have my theta is in 2dB dimension. So I have 2d times capital D many parameters, and my theta is a function of, so my j theta is a function of all these parameters. So what I will do, I take a partial derivative with respect to each of these parameters and accordingly update those parameters. And this is how it will look like. So we are not going in doing the derivation, because that won't be in the scope of this course, but if you are interested you can try to find out, if I derive this from, what update values do I get for different word vectors, how do I update these word vectors. And now once I have done that, I have two different vectors v and v prime, and I can simply sum these over, and that will give me the final embedding for each word. And if you want to understand more about how do we learn these parameters, so you might have a look at this paper, and this gives a nice tutorial for parameter learning. And also if you want to try out an interactive demo, so you can try out here. Now so word2vec is one famous model, and this has two variations, CVOW and skipgram, and both are used. So in some tasks skipgram has shown to be better, and some others CVOW has shown to be better. And there are many other tricks that are used for learning these parameters that we have not covered. I have only tried to give you the intuition. So I hope you will at least have an idea that how these word vectors are learned from my data, by just predicting neighboring words from the context word or context from the neighboring word, and what is the embedding. So how these weight vectors form my embeddings. So now there are some other models. So one other popular model is globe model, okay. And so what is the basic intuition of globe model? So in skipgram, so I am trying to learn my all my embeddings from scratch, okay. So in globe model, what they are saying, so from a corpus you can kind of count the co-occurrences. So you know which, so that's what we did in the distribution semantics, we were counting co-occurrences. Now what they are saying, so this gives a very good idea about the words, so which words are similar to what other words, and suppose you find out what is the co-occurrence probability for any two words. Now try to make word vectors such that when you do a dot product between two words, you get close to the actual co-occurrence that you are seeing in the corpus, and by doing that you will get a low dimension representation, and also it will take care of the words that are coming very sparsely, where you did not have enough data in the corpus to predict the co-occurrence. And this is the simple objective function. So that is, if you look at the objective function, so forget about f is a simple function that makes sure that if certain words are, certain co-occurrences are very, very popular, you do not bias your learning towards those. So you just clip those at certain point. So everything above that will be converted to this one. Now so this is the main idea here of this globe vectors. So you are having in word representation for I and j that you want to learn. An idea is try to learn them that such that they are resembling their whatever you get from the co-occurrence probability. So Pij is from the co-occurrence. You can use either PMI, condition probability, or many other things. So find out Wi and Wj such that they are close to this co-occurrence probability, and then we have this objective function, and you optimize this objective function and try to learn your different weights. So you are trying to combine the best of both worlds, using the count based methods and the direct prediction methods, and using both of these you are trying to come up with your word vectors. And these vectors have also become very, very popular because the training is much more faster than my scriptgram model, because now you are not going to the each individual word in your and all the windows. You have already completed the counts. Now you are only looking at the pairs, word pairs, and maximizing that. And so even with the small corpus and small vectors, they have shown very good performance. So one good thing is that suppose you want to use these vectors for any of your tasks. So either word vectors or globe vectors are freely available on different websites. So word2vec, we already told the website in the previous lecture. For globe, you can go to this Stanford website, and there you can download code as well as the vectors. And these vectors you can use for many of your tasks where you are trying to find out whether two words are similar, or you are trying to find out some analogy task. A is to B, then C is to what, and many other applications they have been used in. So I think this is what I had to say for this topic of distribution semantics. This is a very well growing research field, and lot of new things are happening. So I hope whatever we have discussed will help you to also understand the papers in this field if you want to go in further depth, and also you can try out these ideas for many of your applications. So in the next week what we will do, so we will start with a separate notion of semantics, that is lexical semantics. So how to use lexicon to find semantics between words. Thank you.